several colleagues of ours will come. I will just recall here what I've been doing in the last days. So I had M in B of H with psi naught in H B cyclic. And we had a cone PS, which is M plus psi 0, and another cone PS star, which is equal M prime plus psi 0, like that. And these are closed convex cones, dual to each other. Okay, then what we had that delta 1 over 4 of PS is equal delta minus 1 over 4 PS star. This is obvious from these two things. And then you have also the closures, which are equal, and this is again a self-polar convex, closed convex. We know that if zeta is in P, then J zeta is equal zeta. And moreover, that if X is in M, then X, J, X, J, P is included in P. These two things, together with the anti-isomorphism defined by J, qualify M as a hyperstandard algebra. And what we've been proving up to now is the fact that if zeta is in H and J zeta is equal to zeta, then there exists unique zeta plus, zeta minus in P, such that zeta is equal zeta plus minus zeta minus, and zeta plus is perpendicular on zeta minus. Another result I will remember is that if you have M, H, J, P hyperstandard, and if you have a psi naught in P, which is bicyclic, then, say J is equal J0, P is equal P0. That means the hyperstandard structure is associated to this psi 0 like there. And a last result I will recall is that the following map from self-adjoint elements in M, taking an A to delta 1 over 4A psi 0 in the set psi equal to G psi, such that there is a lambda bigger than 0 with a property that minus lambda psi 0 is less than psi is less than lambda psi 0, that this thing is a bijection. For j eta is equal to eta and j psi is equal to psi, we wrote psi is less than eta, in the sense that at eta minus psi belongs to P. So this is the meaning in here. Now, let me mention two other simple results. Namely, consider E in M a projection. E different from 0. Then the central support of J, E, J, is equal to the central support of A, so that it follows that, because this is in the commutant and this is in E, it follows that E, J, E, J, let's denote it by Q, this is different from 0. And the map from M sub A to M, I will put first so E, and then G, A, G, so MQ. This is a star isomorphism, because it is an induction by a projection with central support equal to the central support of E. Okay, and now what you have that JQ is equal QJ, and QP is equal EJAJP, which is included in P. So that the algebra M sub Q, say, in B of Q of H will be still hyperstandard if I assume that M is hyperstandard with J and P. Then also this one will be hyperstandard with Q, J, Q as a J and QP as a P, as a cont P. Now, this remark is obvious. The meaning of this remark is that in some occasions, using this remark, we can reduce proof to the case where M is countably decomposable. We will see this when we will obtain it. And a last thing that I will not recall, but mention here again, for every projection, E in M projection, there exists a sequence psi n of vectors in P, not such that P psi n is different from 0, and such that E is equal the sum over n in I of P psi n. Now, I put here n, but this is not necessarily a countable set. This is just n in some I. However, if M is countably decomposable, well, if E is of countable type, then there exists a psi in P such that E is equal to P psi. Why this thing? Because the vectors psi n being in P, you have that J of psi n is equal to psi n. So that if the P psi n are mutually orthogonal, then also the P prime psi n are mutually orthogonal. And if EOS is of countable type, we can take the norm of each psi n is equal to 1, and then we take psi, it's equal sum of 2 to power minus n of psi n. And this will be the psi in here. Because the fact that if these are orthogonal, then also P prime Cn are orthogonal, and this is because this equality in here. So in particular, if M is countably decomposable, you will get 1 instead of E, and what you get that there exists psi in P bicyclic. Because you have P psi is equal to 1 according to this conclusion, but because J psi is equal to psi, you have also P prime psi is equal to 1. Well, this is what we did. These are two simple remarks. And now let's go further. There is the following proposition, that if you have psi and eta in P, then you have psi minus eta square is less than the norm of the omega psi minus omega eta, and this is less than psi minus eta times psi plus eta. For the second inequality, this is very easy, is the fact that you have that omega psi of x minus omega eta of x. Oh well, this is 1/2. Let me write it so. Psi plus eta, psi plus eta plus, I'm sorry, x psi minus eta, psi minus eta. So that this inequality is now obvious. Okay, now for the first inequality, assume first that psi plus eta is separating and cyclic, is bicyclic. Well, P psi plus eta is equal to 1, because this implies also that P prime psi plus eta is equal to 1. Just because psi and eta are in P, so they are stable to J. Okay. Now, what we have the following thing. Psi minus eta is bigger than minus psi plus eta, is less than psi plus eta. And now look at the assertion in here. You see a vector between psi naught and psi naught, minus psi naught and psi naught. This was a bicyclic vector. There we assumed that psi plus eta is bicyclic, and then it follows that there exists.
Don't you assume that x of the J invariant?
Sorry?
Hmm? Oh, sorry, they are J invariant. No, go ahead.
How do you get the inequality?
This inequality? Because if you have positive numbers, you have this inequality. Psi and eta are in P. And the inequality means, okay, so that there exists then an A in M. I apply exactly that thing there, such that A is self-adjoint between -1 and 1, and we have that psi minus eta is equal to delta 1/4 of A psi plus eta. Okay. Then we have the following thing, that the norm of omega psi minus omega eta is bigger than, of course, the value omega psi minus omega eta in A. Well, you can put also the modules, but it's a real number, so it's sure that is this. This is the real part of A psi plus eta times psi minus eta, and this is A x psi plus eta is delta -1/4 of psi minus eta. So this is delta -1/4 psi minus eta times psi minus eta. But because we have that J delta 1/4 is delta -1/4 J, I can write that this is equal to delta 1/4 psi minus eta psi minus eta. Why is this? Because psi minus eta is equal to J applied to psi minus eta. So what you have here is delta -1/4 times J. Then this is J, which goes in the other side. That's okay. And it leaves. So that what we have that omega psi minus omega eta in norm, it's bigger than 1/2 of the sum of these two things. So it's delta 1/4 plus delta -1/4 psi minus eta psi minus eta. Okay, and now t plus 1/t is bigger than 2, I think, right? So that this is an operator which is bigger than 1. So this is bigger than psi minus eta square. And that's the end of the proof. In the case, we assume that this is bicyclic. Now let's pass to the case, to the general case, where you don't assume that psi plus eta is bicyclic. So we pass to the general case. And namely, we assume that 1 minus p psi plus eta is different from 0. This is a projection which is different from 0, so that we can find psi such that the projection being p psi. Well, psi is busy, so that I can find a zeta in P such that P zeta is equal to 1 minus P psi plus eta. Okay. And now consider the following vectors. Psi n is equal to psi plus 1 over n zeta, and eta n is eta 1 over n zeta. All these vectors are in P, because eta, zeta, and psi are in P. And then what we have that P prime of psi n plus eta n is equal to P prime of psi plus eta plus 2 over n zeta. And now you see p zeta, that means p associated to 2 over n zeta is equal to 1 minus p zeta plus eta. This relation implies that also p zeta is equal to 1 minus p prime c plus eta. And then this thing is equal to P C plus eta plus P zeta, which is equal to 1. So that what you see in here, you see that this vector is a, what is this? This is a cyclic vector, so it's also separating because it is in, it's stable to J. And so that we are in the first case, the case already considered. And so that we have that P psi n plus eta n, it's equal to 1. By the case already considered, we have that omega psi n minus omega eta n is bigger than psi n minus eta n square. Well, you go with n to the infinity, and you get exactly this inequality. So this is clear, and then what you see from here is that the correspondence from a vector in P to the corresponding vector state is a homeomorphism. Because of this, is a homeomorphism with respect to the norms. Well, we will see that it is a homeomorphism on all positive forms. So that let me record also this result here, namely that for psi and eta in P, we have that psi minus eta square is less than omega psi minus omega eta in norm is less than psi minus eta psi plus eta. Okay. I will write here also first another result is that for psi and eta in P, you have that first thing. You have that psi is perpendicular on eta if and only if P psi is perpendicular on P eta. The second thing is that if you have a zeta in P, and if you have the following implication, zeta perpendicular on eta implies zeta perpendicular on xi, zeta perpendicular on xi, okay, then you have that p psi is less than p eta. And the third thing is that if you have psi is less than eta, then also the projections corresponding p psi is less than p eta. Well, if you have psi perpendicular on eta, then you have the following thing. You have that omega psi minus omega eta is bigger than psi minus eta square, and this is equal to psi square plus eta square, because they are perpendicular by assumption. And this is the same thing as the norm of omega psi plus the norm of omega eta. Now this equality, this inequality here shows obviously that the support of omega psi, not obviously, but it's a classical result, is perpendicular on the support of omega eta. That means you have that p psi is perpendicular on p eta, because this is the support of omega psi and this is the support of omega eta. Now, this implication here follows now obviously from this thing, because if this implies this, it follows that if p psi is perpendicular to p eta, it implies that, what did I write here? I'm sorry. Zeta, and here is also zeta. If p zeta is perpendicular on p eta, then also p zeta is perpendicular of p psi, so that p psi is less than p eta, because you have to use again this observation, this remark. Okay. And good. And now the last thing is the last thing is a consequence of this thing here. Because if you have psi less than eta, you have also the fact that what is okay, if you have this relation here, then you will have the fact that 0 is less than zeta eta is less than zeta psi zeta eta zeta. So that's clear. And then if you have this thing, it follows that if this is 0, then also this is 0, so that you get this conclusion. And this conclusion implies p psi is less than p eta. So that we have also this result. As a corollary, As a corollary, let me write it here in order to have all the results. The corollary is that the mapping from P, taking xi and going to omega xi, is a homeomorphism of P onto a closed subset of M star plus. And it will remain to show that it is surjective in order to have the correspondence I announced yesterday. But now let's see this result. It's clear by the proposition we proved here, it is clear that the map psi going to omega psi is a homeomorphism with respect to the norm topologies. This belongs to all omega zeta with zeta belongs to P in M plus star. And this is homeomorphism because of the two inequalities we had. Okay. Now, suppose you have omega psi n with psi n in P. Suppose omega psi n is a Cauchy sequence in norm. Then also psi n in P is a Cauchy sequence because of the same inequalities. Now P is closed, so this psi n converges to a psi in P. And again, the proposition shows that you get omega xi. Omega xi, which is the limit of omega psi n. So you took a Cauchy sequence and you found a limit of it. So that the image here is closed. And that was the assertion.
So, but this has a meaning only when M is not countably decomposable.
Sorry?
This one has
Meaning.
sense when M is not
Yes.
countably
Yeah.
decomposable. Otherwise, the full set. Range is the full set.
Is the full set, but not with psi in P.
Well, but when you have hyper standard form and every positive linear functional is given by the
Yes, but
element.
exactly this I have to show. This is what I intend to show, that every positive form is a vector form with a vector in P.
I'm sorry that I'm still
Okay, so that what you said is, we already have seen it as a third form of the spatial theorem of von Neumann, but we will arrive also there. So, let me write also here in order to have all the results here. You have a psi 0 in P. And then, for every normal form, positive form on M, such that phi is less than omega psi 0, then there is an eta in P such that you have phi, phi, it's equal to omega psi 0 eta plus omega eta psi 0 with eta less than psi 0. This is what we have to prove. Okay, let's prove this thing. Is the last intricate proof. Proof. So, by assumption, everything happens under the support of omega psi 0. The support of omega psi 0 is a countably decomposable vector. So that by the gadget we put here, this one, we can reduce the problem to the case of countably decomposable algebras. So that we may assume, without loss of generality, that psi 0, that the support of omega psi 0 is equal to 1. And then that means that P psi 0 is equal to 1. Psi 0 is in P, so that also P prime psi 0 is equal to 1, because psi 0, it's J psi 0 is equal to psi 0, and so that psi 0 in H is bicyclic for M. Okay. We denote by S and delta the associated operators for these bicyclic vectors. And what we know from this thing, we know that also the others, J and P, are associated to psi 0, because psi 0 was in P. Okay, so that we have also J and P associated to psi 0. Okay. Now, there is among the Radon-Nikodym theorems, there is one which is very simple, namely with the so-called derivative in the commutant. More precisely, because I have that phi is less than omega psi 0, then there is an element A prime in the commutant, 0 less than A prime less than 1, such that phi of x is equal omega of psi 0 is x psi 0, A prime psi 0. Okay. Then A prime psi 0 belongs to P S star, because this element is in M prime in the commutant. And the same way you have 1 minus A prime, because A prime was positive here, and 1 minus A prime is also positive here. It belongs also, psi 0 belongs also to P S star. Okay, that's what we have. Let zeta be, by definition, delta minus 1 over 4, A prime of psi 0, which this belongs to P. And also put then psi 0 minus zeta is equal delta minus 1 over 4, 1 minus A prime psi 0. Because Well, and this belongs also to P. The fact is that psi 0 is stable to delta. Now, we have to find the eta for the statement. We define eta as being, by definition, it's equal to 1 plus delta 1/2 minus 1 of A prime psi 0, which is equal to, if we look at this equality here, this is equal to 1 plus delta 1/2 to minus 1 of delta, I put it in the other side to get the A prime psi 0, delta 1/4 zeta. Okay. Now, for such an operator, we had a formula as a consequence of the theorem of Van Dahl, which used the residua theorem. And namely, let's put f of t is the function 2 over e to power 2 pi t plus e to power minus 2 pi t. And then that result, that corollary of the theorem of Van Dahl, was saying that eta in here actually, it's equal to integral from minus infinity to infinity of f of t delta to power it of zeta dt. Okay. Now, what we have? We have that 0 is less than zeta is less than psi 0. Yeah, because this was in P. Is less than psi 0. And then what we get that 0 is less than integral from minus infinity to infinity of f of t delta power it of zeta dt. It's less than integral from minus infinity to infinity of f of t delta power it of psi 0, which is equal to psi 0. So that what we get the fact that this guy here, eta, is less than psi 0. Okay, now, on the other hand, I have also j eta is equal to eta. And then we have that A prime psi 0, which is equal to 1 plus delta 1/2 of eta. This is from this relation in here. It's further equal eta plus, I write delta power 1/2 under this form, S star j of eta. And because j of eta is equal to eta, this is eta plus S star of eta. Now, for any x in M, we have the following chain of equalities. Phi of x is equal to x psi 0, A prime psi 0. This was exactly how A prime was chosen, but by that Radon-Nikodym theorem. This is equal to x psi 0 times eta plus x psi 0 times S star of eta, because A prime psi 0 was equal to this thing in here. Now this is further equal to x psi 0 eta plus eta x star psi 0. I just went with S in the other side, but I had to change the order. So eta x star psi 0. So this is equal to omega psi 0 plus eta. This is this thing here. Plus, this is obvious. I put the x star from here. I put it in here as x. So this is omega eta psi 0. And this means exactly what was asserted. Say it.
I'm sorry, but why eta less than equal to J0 and
Why what?
That equation on the left.
Here.
Yes.
This one.
Yes.
This one is because this belongs to P.
why eta less than equal to J0?
So this was the problem? No.
Eta, the line above.
So where?
Eta less than equal to J0. In the square bracket.
Eta is less than psi 0. This one is the problem. Let me see it. Also, eta is less than psi 0. Let me see where it is. Okay, this is eta, right? This was eta.
Yeah,
Eta is this, is this, is this,
yeah.
right? Okay, this is eta. And this is psi 0, right? Because delta IT of psi 0 is always psi 0, and the function there has the integral equal to 1. So that eta, which is this one, is less than psi 0. Is that okay? Is that okay? Fine. Okay, so we got also this result in here. Okay. Now, what I still have to show is that every normal positive form is a vector form with a vector from P. And the integrals were in this order here because P is closed. So, I take psi 0 in P, and I take a positive form, phi, normal positive form, less than omega psi 0. Then I show that there exists a vector psi in P such that phi is omega psi. So that this is exactly what I had to prove. So that the proof in here is the following. Take phi 1, it's equal to omega psi 0 minus phi, which is a positive form. And apply the last result there to this form here. It follows that phi sub 1 is equal to the vector form omega psi 0 eta 1 plus omega eta 1 psi 0 with a vector positive eta 1 less than psi 0. Less than psi 0. This is the reason. Okay, and let's denote psi sub 1. It's equal to psi naught minus eta 1, which belongs to P. Then it's easy to check with all these things here that omega psi 1 minus phi is omega eta 1. And what we still have here is the fact that phi 1, the norm, is a positive form, so this is phi 1 of 1. So this is this applied to 1 is psi 0 eta 1 plus the conjugate eta 1 psi 0. So that what you have here, it's 2 times the real part of psi 0 eta 1, which is 2 times psi 0 eta 1, because both psi 0 and eta 1 are in P, so that this is bigger than 0 and also accounts for this equality I put there. Now, what we have is the following. We have that in P I have eta 1, which is less than psi 0. And this implies that eta 1 is less than psi 0 eta 1. Okay, because the cone P is self-polar. Okay, and as a consequence of this, we get that omega psi 1 minus phi is equal to the norm of omega eta 1. Okay, this is eta 1 square. You have here you have it here, which is less than 1/2, which is less than this, but this appears here. This is 1/2 of norm of phi 1, and this is 1/2 of omega psi 0 minus phi. Okay. So what we obtained with vectors in P, we obtained this inequality. Now, what we can do, we can repeat the argument with psi 1. And I will get a psi 2, such that omega psi 2 minus phi it's less than 1/2 this one. So that what I get a sequence psi n in P, such that I have omega psi n plus 1 minus phi is less than 1/2 omega psi n minus phi. So this thing goes to 0. So that omega psi 1, psi n minus phi converges to 0. And that means that also there exists a psi in P such that phi is equal omega xi. I want to show to you the result in here. Not this one. I didn't record the result here, but we proved that the mapping psi going into omega psi is a homeomorphism of P onto a closed subset of the positive part of the predual. And this was already proved in here. So that also this statement, the statement put up there, is proved. Okay. Now we have the main result, theorem. I think this theorem is due to Hagerup and perhaps independently also Kohn. And this is the following thing. If you have M in B of H, a hyperstandard algebra, with J and P, then the mapping psi is going into omega psi. It's a homeomorphism of P into M star plus homeomorphism with respect to norm topologies. Okay. The only thing, proof, that remained to be proved is the fact that the set omega psi with psi in P is norm dense in M star plus. Okay. We may assume, I will not skip the details here, we may assume that M is of countable type. Then, there exists psi 0 in P, be cyclic. It's this result in here, applied to the identity projection. There is a bicyclic vector in P. Now, the set omega xi with xi in P contains the set phi in M star plus such that there is a lambda bigger than 0 with phi is less than lambda omega xi 0. You can see on the other blackboard the corresponding result which ensures us this conclusion. Okay. So that if this contains this, and I want to show that this set is dense, it's enough to show that this set is dense in M star plus. Okay. So that let phi belonging to M star plus. Then, by the spatial theorem of von Neumann, there exists a vector eta in H, which is equal to M psi 0 closure, such that phi is equal to omega eta. So we applied the spatial theorem of von Neumann under the third form, I think, or so. Okay. It follows that there is a sequence. Well, this is M psi 0 and it's also M prime psi 0, and I want to use M prime psi 0. So there is a sequence x prime n in M prime such that xn prime psi 0 converges to eta. Then, of course, also omega xn prime psi 0, I'm sorry, psi 0 in here, will converge to omega eta, which is our phi. But now, each such form satisfies this. It's obviously. With lambda, the square of the norm, omega xn prime psi 0 is less than the norm of xn prime times omega psi 0 square. So these are indeed dense in phi, in M prime. So what we have is the fact that every normal positive form is in a unique manner and in a homeomorphism manner a vector form with a vector in P, in the cone. Right? Okay. I still have 20 minutes. Is that okay? Yeah. Okay. So I already defined yesterday what is the spatial derivative in this case. And as I said yesterday in the afternoon, there are two completely different notions with the same name, spatial derivative. So I will do some more things here perhaps. And tomorrow I will try to give an exposition without proofs of the construction of the spatial derivative used by Professor Takesaki and of the main properties as stated by Alain Cohn. So today I have to prove just one more thing. Let me erase the blackboard. So this is the following statement, which is a corollary of the theorem I proved. Is the following thing, corollary. You have mk in B of hk hyperstandard with jk pk, so k is equal 1 and 2. Okay, you have p defined on M1 with values in M2, a star isomorphism. Then we know that this star isomorphism is implemented by a unitary. But what is said here is the fact that there exists a unique unitary operator U from H1 to H2, unitary, such that P of x1 is equal U x1 U star for x1 in M1. The second commutes the G's. G2 is equal to U J1 U star. And 3, P2 is equal to U of P1. And with these properties, this unitary is unique. So it's what I said yesterday. Any star isomorphism, that two hyperstandard forms as uniquely unique. Okay. Now, proof. I have to prove first the uniqueness. Okay. From the statements there, 1, 2, 3, it follows that for every psi1 in P1, we have omega u psi1, it's equal to omega psi1 composition with pi. We could do it pi to minus 1 to respect the... and u psi1 belongs to P2. Okay. By the previous theorem, the theorem is showed, it follows that this thing is uniquely determined with this property in here. Now, H1 is the linear envelope of P1. That's it. So that the uniqueness is obvious. Now for the existence. For the existence, well, we assume first that M1 is countably decomposable. And then we can go to the general case. I will do only the countably decomposable thing because the other one is some blah blah. It's easy. So that M1 of countable type okay, if M1 is of countable type, it follows that M1 has a bicyclic vector psi1 in P1. It's just that lemma which shows that for every projection there is a vector such that E is P psi. Okay. By the previous theorem, there exists a unique vector xi2 belonging to P2 such that omega xi2 is equal omega xi1 composition with P minus 1. Okay. I don't have my cheat sheets. Here should be. Okay. Now, it follows that Xi2 is separating for M2. Why? Because this was a bicyclic vector, so that omega xi1 was a fightful vector form, so that because this is an isomorphism, this is also a fightful vector form. So the support is equal to 1. So the vector is separating for M2, but because it's in P2, so it's stable to J, it follows that it's also cyclic. So that this is bicyclic for M2. Now we have the relations as follows. U of x1 xi1 is equal to pi of x1 xi2. This relation defines a unitary operator U from H1 to H2, which will be the one we are looking for. Okay, this satisfies obviously this relation here because of the definition. Okay.
Where you U unitary?
Sorry?
Where is that U unitary?
Because pi, well, norm of x1 xi1 is equal to the norm of pi of x1 xi2. It's just an isomorphism here. So that what you get, well, if you want to get more, we get more. We have this thing. No, it's because of this relation. It's because of this relation in here. This means if I put here the squares, this means x1 star x1 xi1 xi1, and what is here? It is pi of x1 star x1 xi2 xi2. So it's omega xi2 composition with pi, and this is omega xi1. And because they are equal, these are equal, right? Okay? Good. So we defined a unitary here. And, well, the S operators have concrete descriptions. S of x xi0 is x star xi0. So that using this, it's easy to prove that S2 is U composition S1, composition U star. And this means we have also the second. This implies also the second equality there. And the last thing, it's simple, P2, it's equal to x2 j x2 j, which x2 in M2. That means this is x2 is u x1 u star times etc. So that you arrive immediately at the equality. The u will exit from the picture. So this means that, fine, I have still 10 minutes to end the whole story. So that indeed two hyperfinite forms are uniquely unique. So that I have to prove just one more thing to end this whole story. Namely, by the last theorem, we have a map from the automorphisms of M, sigma, an automorphism of M, to U sigma, which is a unitary in H, where you assume that M included in B of H with J and P is hyperstandard. Okay. The main thing is the following. This will be denoted by named canonical implementation. With the three properties in there. Okay, and then this canonical implementation is a homeomorphism, an isomorphism of topological groups What topology? On U of H, you can take the SO topology, which is the same as the VO topology. On the automorphism of M, we consider the topology defined by semi-norms sigma is going into norm of phi composition with sigma. And this for every phi in the predual of M. So the topology defined on the automorphism of M is the topology of uniform convergence on the predual. And this is an isomorphism of topological groups. So that let sigma and sigma I be automorphisms of M. Sigma I is a net. Then sigma I converges to sigma in automorphism of M with that topology. That means that the norm of phi composed with sigma I minus phi composed with sigma goes to 0 when I is in the directed setting. Now, this is if and only if we have, this is for every phi belonging to M star plus, actually. That means omega psi composed with sigma I minus omega psi composed with sigma goes to 0 for every psi in P. Oh, that means that omega psi let me denote, so sigma is add u, and sigma I is add ui, with the u's given by the canonical implementation, so that you have that ui star psi minus omega of u star psi converges to 0 for every psi in P. That means, because of the theorem we had, that because the correspondence psi goes into sigma psi, the correspondence psi in P goes to omega psi in M star plus. This correspondence is continuous, bicontinuous. Then we have that ui star psi minus u star psi converges to 0 for every psi in P. And that means actually for every psi in H, because P, the linear hull of P is the whole H. That's it. That's exactly the, well, star convergence, but it's nothing. It's okay, right? So that, indeed, the natural topology on automorphism of M is defined by this proposition. This will be the natural topology on out of M. Is the topology of uniform convergence on the predual, because you don't need lots of sophistications in order to define this. But it's the same thing that in the canonical implementation, the implementing unitaries will converge weakly to